Okay, in this video, we want to finally start solving for the volume of different surfaces of revolution. And to get us started, we picked a rather basic problem because it's our first problem, and also because there are several different things that we'd like to demonstrate with this problem. So here's the setup. We have a curve, y equals x squared, and a line y equals 9. We're interested in the region between the curve and this line, and we're going to rotate it about the y-axis to give us a three-dimensional figure. And we're going to find the volume of it. And once we do that, we're going to rotate it not about the y-axis, but a different vertical line where x is equal to -2. And you see how that changes our volume integral. And then we have a third vertical line we're going to rotate it about to see how, again, that changes our volume integral. So let's get started. Obviously, this is the curve of a parabola. It's just a horizontal line, so it shouldn't be too difficult to sketch out. Here we have the y-axis and the x-axis. Obviously, when x equals 3, y equals 9, so if we have it like this, that's the line y equals 9, and that parabola would be like this. This would be where x equals 3, and this is the line of the curve y equals x squared. It's always nice to label your different curves that you have in your diagram. And let's see, we're interested in the region between the curve and the horizontal line. So that would be this region right here, and this is the x-axis. Here we have the y-axis. I'm going to rotate it about the y-axis to give us our three-dimensional figure. And to find the volume of it, let's say we want to see if we can find the volume using the disk method. Now, remember, when you're using the disk method, you can think of it as creating tiny volume strips, and you do that by drawing your strips being perpendicular to the axis of rotation. So we're going to have horizontal strips like this. Each with a thickness of dy. And we pointed out in some detail in our introductory video that with this kind of a setup, the volume integral, I hope you've had a chance to look at those introductory videos, the volume integral is going to be equal to pi, the integral of x squared dy. And basically what's happening is this. When we rotate this curve about the y-axis, this horizontal strip is also being rotated about the y-axis, and that gives us a solid circular disk that has a thickness of dy. And it'll have an area equal to pi r squared. R is the radius. And here the radius of the disk, that's just going an x distance away from the origin, whether the disk is here, or up here, or down here. Its radius is just x. So for each one of these circular disks, it would have an area pi times x squared and a thickness of dy. So for each one of these circular disks that we're making, it would have this volume, and we would add up the volume of all these circular disks, starting down here at y equals 0, and going all the way on up to where y equals 9. So we would have, for our limits, y equals 0, y equals 9. So that's a setup for the problem, but we're not ready to solve it yet because we're integrating with respect to y and here we have an x squared. So here again is why it's useful to label your curves. We're going over here to this curve here, and at the curve x squared is equal to y. So we can rewrite the integral then. The volume will equal pi, and the limits stay the same, those don't change, except we have x squared as y. So this would just be equal to pi over 2 times y squared. Y goes from 0 to 9, and that would equal 81 times pi divided by 2. And the problem is finished. That would be the volume then of obtained by rotating this about this parabola about the y-axis. So again, we did pick a pretty basic example, but there's several things that we wanted to point out with it. And the next issue being this: suppose that we did not rotate about the y-axis. Suppose we rotated over here about this vertical line that has x equals -2. And we're using the method of disks. So clearly what's happening now is you can think of this, we're forming our horizontal strips. Now we have to go out an extra distance of 2 more units. Like this. So as we're forming our circular disks, they're going to have a new radius. The radius is not just going to be x, it's going to be x plus 2. So now the volume integral will become this. Equals pi. And we're still integrating from y equals 0 to y equals 9. It doesn't change. But now the new radius is x plus 2. 1 squared dy, and we're still integrating now with respect to dy. So we multiply this out, we have x squared plus 4x plus 4, but this will be y. X squared is y. That will be the square root of y, so this will be equal to pi times the integral from 0 to 9 of x squared, that's y, plus 4 times the square root of y, plus 4. And that becomes our new volume integral. So we're not going to evaluate it. You can see it's pretty straightforward. What we want to do is just kind of stress that when you're not rotating about the y-axis, but about a different vertical axis, how you can set up your integral. And let's see here. Let's suppose now we don't have this situation, but instead we're going to rotate it about for x equals 12. So that might be like this, the line x equals 12. Now, here we're forming vertical strips. Excuse me, horizontal strips. They're going to be rotated about this line here. And we want to know, okay, what's going to be the radius? Well, this, let's take this out of here for a moment. This here is a distance of x away from the origin. This line here, this is 12 units away. So this section here is going to be 12 minus x. So our new radius, that's our new radius right there. So now the integral becomes pi. We're still adding up from 0 to 9, that doesn't change. Except here we have 12 minus x squared times dy. And if we multiply this out, we have 144 minus 24x plus x squared. Multiplying this out, that's y, that's the square root of y. So now our new volume integral is this, 144 minus 24 times the square root of y plus y. X squared is just y. So now that becomes a new volume integral. So again, nothing complicated, but we just wanted to take a basic example. We could just kind of work through the steps here. And one more thing to say before we close out the video. When we're setting up the problem, we recognize that this is our region of interest. What happens if we decide the method of disk we tried using shells? Sometimes you can use disk or shells, but you can't use both. We had a video that explained that sometimes you have to look carefully what your region is and the shape of the region, and then decide whether you have to use disks or shells to compute the relative volume. Let's take a look at this one. Suppose that we said, let's try it with shells. Well, then with shells, we draw in strips perpendicular, or parallel to your axis of rotation. There's the y-axis, so we would be drawing shells like this. And we're doing this going from x equals 0 to x equals 3. Looks like that should work out for this figure. So before we go to a more complicated problem, let's go to another video, and we're going to take the same problem, and we're going to try and solve it now using shells instead of disks to see what kind of an answer it gives us. So come back and join us for that video, and then we'll get to some more complicated problems.